Now to the extraordinary images tonight, the scare for visitors at Yellowstone National Park.
In Yellowstone National Park, geologists say one of the park's famous geyser basins now has a new hot spring.
A new development deep beneath the surface of Yellowstone has captured the attention of geologists worldwide. Recently, experts reported the emergence and expansion of a secondary magma plume northeast of Yellowstone's main caldera. This newly tracked geological activity signals a profound shift in the subterranean dynamics of one of the world's most closely monitored supervolcanoes. Unlike the more familiar primary plume that has long fed the caldera's immense geothermal features, this secondary plume represents a fresh chapter in Yellowstone's geological story, one that is evolving in real time and reshaping long-standing scientific assumptions about the region's subterranean forces. Before we start, smash the like and subscribe buttons for more updates. The discovery of this secondary plume came after a series of subtle but persistent anomalies began to register on geological monitoring systems. Seismic arrays and GPS deformation networks detected ground uplift and microseismic swarms that deviated from typical patterns associated with the primary plume. These tremors, though small in magnitude, were unusual in their frequency and geographical distribution. As scientists analyzed the seismic waveforms, they found signatures suggesting the movement of molten rock, specifically a rising column of magma distinct from the main chamber. The plume was first noticed approximately 15 kilometers northeast of the main caldera rim, and subsequent scans indicated it was actively growing and advancing northeastward. What makes this event particularly significant is the unusual positioning and dynamics of the plume. Yellowstone's primary magma source is believed to be fueled by a deep mantle plume that has existed for millions of years, slowly shaping the Yellowstone Plateau. However, this secondary plume appears to branch away from the main upwelling, creating an offshoot that could eventually evolve into its own independent magmatic system. Early readings suggest that this new plume is shallower than the main magma body, hovering between depths of 5 to 12 kilometers beneath the surface. As it continues to rise and expand, it is displacing crustal rock and altering subsurface pressures in the northeast quadrant of the park. This northeastern advance introduces fresh questions about the potential for new geothermal formations. Historically, geysers, hot springs, and fumaroles in Yellowstone have been directly linked to the magmatic heat supplied by the main plume. The presence of a secondary source could eventually give rise to a new network of hydrothermal features, completely separate from the existing system. Early thermal imaging already shows an uptick in surface temperature anomalies northeast of the caldera, corresponding roughly to the location of the ascending magma. These changes, while still in their infancy, may be the harbingers of entirely new geothermal phenomena that could emerge in coming years. Beyond the surface, the secondary plume's trajectory through the Earth's crust presents a challenge to geological models of the region. For decades, scientists believed Yellowstone's activity was governed by a relatively centralized magmatic structure, but this new development points to a far more complex system, potentially characterized by multiple feeding sources, branching conduits, and interconnected magma pockets. The northeastward expansion of the plume might suggest that the magmatic system beneath Yellowstone is not a static or isolated entity, but rather a fluid and evolving network, constantly reshaping itself based on internal pressures and thermal gradients. Another point of intrigue is the role this secondary plume might play in crustal stress redistribution. As magma moves, it exerts pressure on surrounding rock, often altering fault lines and influencing tectonic stress fields. The plume's expansion is already thought to be linked to an uptick in microquake activity, not just directly above it, but in areas several kilometers away. These seismic echoes reflect the interconnected nature of the crust beneath Yellowstone, a tightly knit mosaic of rock, faults, and molten intrusions. Any new influx of magma, especially in an unexpected location, could increase the likelihood of tectonic shifts or cause pre-existing faults to reactivate under new stress conditions. This emerging plume could also provide a unique opportunity to study the life cycle of a magma conduit. Normally, scientists examine fossilized volcanic systems or infer plume behavior from ancient eruptions, but the ongoing development northeast of Yellowstone allows for real-time observation. Using tools like magnetotellurics, seismic tomography, and satellite-based interferometry, researchers are constructing detailed models of the plume's architecture. Early data reveals a vertically elongated column of low-density material, consistent with superheated magma, rising steadily and exhibiting branching toward the surface. This morphology suggests the early stages of what could become a significant magma chamber or a feeder zone for future volcanic or hydrothermal activity. The implications of a secondary plume are not limited to Yellowstone alone. This phenomenon could indicate broader patterns in how magma systems evolve over time in other caldera settings. If multiple plumes can coexist and interact within the same geologic environment, then it's possible that many supervolcanoes around the world harbor similar complexities. Such a realization would require geologists to revisit the assumptions built into hazard models, particularly those concerning eruption forecasts and geothermal evolution. In Yellowstone's case, the presence of this new plume might change the probabilistic risk landscape, not necessarily increasing the likelihood of a major eruption in the immediate term, but certainly adding new dimensions to how such an event might unfold. Adding to the intrigue is the speed with which the plume is advancing. Based on current velocity estimates derived from seismic and geodetic measurements, the plume appears to be moving at a rate that exceeds typical magmatic intrusion speeds in similar crustal conditions. This suggests that it is being driven by a strong thermal gradient and possibly a focused mantle upwelling channeling fresh material from deep within the Earth. If this rate continues or accelerates, the plume could breach higher levels of the crust within years, potentially influencing surface processes far sooner than previously expected. This timeline matters greatly when considering geothermal dynamics and the potential for future surface expressions. An active magma source rising rapidly can heat groundwater to the point of supercritical pressure, triggering the creation of new geysers or even hydrothermal explosions if confined systems rupture under stress. Yellowstone has experienced such events in the past, with crater-like depressions and violent steam releases. The emergence of a new plume could shift the epicenter of such risks northeastward, particularly if brittle rock layers above the plume cannot accommodate the rising thermal and pressure loads. Another aspect being closely studied is the interaction between this new plume and Yellowstone's massive hydrothermal system. The park is home to the largest concentration of geysers on Earth, supported by a delicate balance of heat, water, and chemistry. The introduction of a new heat source could alter the fluid flow paths that feed these features, potentially rerouting or even disrupting their activity. For example, a change in subsurface pressure gradients might redirect boiling groundwater toward new locations, drying out some geysers while creating others. Researchers are already noticing shifts in geyser intervals and behaviors, though it remains to be seen if these are directly tied to the secondary plume or other geologic processes. The northeastward movement of this plume is also fascinating from a tectonic perspective. Yellowstone sits atop a complex transition zone where the North American plate is influenced by both extensional forces and the deeper mantle dynamics of the plume itself. The appearance of a new magmatic conduit in the northeast could signal a form of crustal adjustment or accommodation, where rising magma exploits weaknesses in the overlying rock. This might help explain why the plume has not moved vertically, but rather diagonally, suggesting that the regional stress regime and lithospheric heterogeneity are guiding its path. Monitoring the expansion of the plume involves an array of sophisticated technologies, including deep Earth radar, gravity anomaly mapping, and muon tomography, an emerging technique that uses cosmic particles to image subsurface density changes. These tools are revealing not just the plume's growth, but its temperature gradient and volatile content. Preliminary gas composition analyses from peripheral fumaroles hint at elevated concentrations of CO2 and SO2, both of which are telltale signs of fresh magmatic input. Though still within normal limits, the upward trend in gas emissions reinforces the theory of an active, volatile-rich intrusion feeding into the crust from below. One of the most pressing questions among geologists is whether this plume will ultimately lead to a surface eruption or remain a deep-seated phenomenon. Magma movement alone does not guarantee an eruption. It depends on numerous factors such as pressure buildup, rock permeability, volatile content, and the presence of conduits to the surface. However, the continued rise and northeastward migration of the plume increases the chances of localized crustal melting, dike intrusion, or even the formation of new volcanic vents if conditions align. These possibilities are being modeled with increasing urgency, as understanding the trajectory and behavior of the plume is essential for refining risk assessments and early warning protocols. Long-term, this secondary plume may evolve into an entirely new magmatic center. Over geological timescales, such plumes can form batholiths, large underground magma reservoirs that cool and solidify into granitic rock. Alternatively, if the pressure and heat remain sustained, the plume could give rise to a new volcanic complex, independent of the existing caldera. Yellowstone's geological record contains evidence of ancient eruptive centers that predate the current caldera system, suggesting a history of shifting magmatic activity across the region. The newly discovered plume might represent the early stirrings of a similar transition, slowly laying the groundwork for future geologic epochs. The ecological implications are also notable. Yellowstone's unique biodiversity owes much to its geothermal underpinnings, and a shift in the subsurface energy landscape could have cascading effects on microbial ecosystems, vegetation zones, and thermal habitats. The northeast section of the park, currently less active thermally, might begin to exhibit new hot zones, attracting thermophilic organisms and reshaping the local ecology. Scientists are already preparing for expanded biological surveys to monitor any changes in microbial activity or soil chemistry as the plume continues to evolve. In light of this, interdisciplinary collaboration is intensifying. Geologists, biologists, chemists, and climate scientists are pooling their data to develop a comprehensive picture of the implications this new plume might have. These efforts are not only focused on Yellowstone, but also on building a broader understanding of how magma systems interact with the Earth's surface across various environments. The lessons learned from this unfolding event will likely inform future studies of volcanic regions from the Andes to Kamchatka, providing a unique comparative model grounded in active observation. The emergence of this secondary magma plume northeast of Yellowstone's caldera represents one of the most intriguing geologic developments in recent memory. Its expansion is not just a matter of academic interest, it is a window into the ever-changing processes that shape our planet from the inside out. As it grows and shifts, the plume is rewriting what scientists thought they knew about Yellowstone's magmatic architecture. It is a stark reminder that beneath the park's scenic beauty lies a dynamic and restless Earth, constantly in flux and full of surprises waiting to rise from the deep. The unfolding development of the secondary magma plume northeast of Yellowstone's caldera is ushering in an era of increased scrutiny and sophisticated exploration. While the foundational discovery has already sent ripples through the geological community, the ongoing analysis has begun to reveal layers of complexity that suggest this event may be one of the most consequential subterranean shifts in Yellowstone's recent geologic timeline. The dynamic nature of magma movement in the crust is now observed with unmatched clarity thanks to innovations in subterranean imaging and thermodynamic modeling. And the implications of this new plume continue to deepen with every passing day. One of the most compelling aspects of the plume's progression is its deviation from symmetrical central magmatic upwelling. Typically in hotspot volcano systems like Yellowstone, magma rises vertically through weaknesses in the lithosphere directly above the heat source in the mantle. The path of this new plume, veering northeastward instead of following the vertical trajectory of the central plume, suggests significant tectonic and lithospheric variability in the northeastern portion of the volcanic plateau. This path of least resistance is shaped not just by heat and pressure but also by ancient fault lines, buried rift structures, and compositional differences in the crust that are now being brought into focus through high-resolution geophysical surveys. A growing body of research is focusing on how this divergent plume trajectory correlates with crustal discontinuities that date back tens of millions of years. Subsurface mapping efforts have recently detected low-angle detachment faults and sheared metamorphic layers in the northeastern Yellowstone terrain, likely vestiges from older tectonic regimes. These structures may now be reactivating or accommodating stress to form conduits that allow the magma to snake laterally as well as vertically. This idea redefines the assumed plumbing system of the region, pushing geologists to adopt a more distributed model for magmatic intrusions, where lateral propagation plays as important a role as vertical ascent. In tandem with geophysical monitoring, geochemical analyses are revealing new insights into the composition of this plume. Melt inclusions, gathered through xenolith samples brought to the surface via minor eruptions and geothermal vents, are showing subtle but notable differences from the primary magma chamber beneath the caldera. The magma sourced from this northeast plume contains slightly higher levels of potassium and thorium, elements associated with more evolved magmas. This suggests a longer residence time within the crust, or perhaps more significant interaction with the surrounding rock. Such interaction could change the behavior of the magma dramatically, potentially making it more viscous, more gas-rich, and in certain cases, more explosive under specific pressure conditions. Thermobarometric modeling based on these melt inclusions shows that the magma in this secondary plume is crystallizing at different pressures and temperatures than that of the main chamber. The result of this distinction is not merely academic. It points toward the existence of a separate magmatic system forming within Yellowstone, one with its own unique thermodynamic profile. In volcanic terms, this could mean that future activity sourced from the northeast might not mirror the style or scale of past eruptions from the central caldera. It might, instead, produce smaller, more frequent dome-building eruptions, or perhaps trigger extensive hydrothermal outbursts before any full-scale volcanic expression takes place. As magma intrudes into cooler crust, it generates intense thermal and mechanical stress on the surrounding rock. The stress field resulting from the new plume is now under detailed simulation, and early results show concentrated zones of potential failure in a radial pattern northeast of the caldera. These zones of weakness are particularly susceptible to future dike formation, in which magma injects horizontally through rock layers, creating sills and increasing the likelihood of surface deformation. Uplift signatures consistent with sill emplacement are now being recorded in topographic and INSAR interferometric synthetic aperture radar data over a wide area east of the Lamar Valley. These minute changes, often just millimeters per year, speak volumes about the subsurface dynamics underway. Equally fascinating is the plume's interaction with subsurface aquifers and trapped groundwater systems. As the magma body moves into zones saturated with water, it superheats the fluids, potentially creating volatile-rich pockets that can become explosively unstable. Hydrothermal systems rely on equilibrium between water pressure and geothermal input, and even small changes in subsurface temperature or pressure gradients can destabilize the balance. The northeastward advance of this plume threatens to do just that, particularly in areas where faults act as both heat and fluid conduits. The result may be the sudden development of phreatic explosions, non-magmatic steam blasts that can occur with little to no warning, scarring the surface and radically altering the local landscape. In light of these discoveries, the U.S. Geological Survey and other monitoring organizations have begun to intensify their focus on the northeastern portion of Yellowstone. New borehole arrays and mobile seismic stations are being deployed to track even the faintest signs of magma intrusion. These efforts are augmented by autonomous drone-based sensors that can collect gas samples and thermal images from areas too remote or hazardous for regular fieldwork. The synergy of ground-based and aerial surveillance provides a continuous feedback loop of data, allowing for real-time analysis of the changing geological conditions. At the same time, environmental scientists are examining the ripple effects of this subsurface activity on the surface ecosystems. Yellowstone is an intricate web of biological zones, each delicately balanced by climate, geology, and hydrology. As magma creeps closer to the surface, even in the absence of an eruption, it alters the soil chemistry, releases trace gases, and changes the temperature of underground water that feeds streams, wetlands, and hot springs. These changes can lead to shifts in plant distribution, insect behavior, and microbial populations that thrive in thermally active soils. Such transitions are already being recorded in microbial mats and thermophile colonies that appear to be migrating in response to shifting heat flows. The long-term implications for landscape evolution are equally profound. A rising magma plume has the capacity to gradually uplift large portions of the crust, much like a slow-motion bubble forming beneath the surface. This uplift can create new fault lines, tilt drainage patterns, and even disrupt existing river courses. In Yellowstone's northeast, such geomorphological changes could alter the trajectory of the Yellowstone River and its tributaries, with cascading consequences for erosion, sedimentation, and floodplain dynamics. Landscape models suggest that within the next century, certain low-lying regions in the northeast may become significantly more elevated or fractured, possibly giving birth to new geothermal basins or altered catchment zones. Another emerging field of research focuses on how the new plume may influence Yellowstone's broader volcanic arc. Though often studied in isolation, Yellowstone is part of a much larger tectonic and magmatic system that spans from the Snake River Plain in Idaho to the Rocky Mountains. Magma movement in one part of this system can resonate throughout the network, redistributing stresses and influencing volcanic activity elsewhere. Researchers are now studying potential correlations between this new plume activity and subtle seismic adjustments in regions far beyond the park's boundary. If a connection is confirmed, it would redefine how geologists understand the region's magmatic coherence and tectonic integration. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Yellowstone's secondary magma plume expanding northeast right now? We want to hear from you. Thank you for watching, and see you next time.